Good morning, students. Yesterday we discussed Weingarten equations regarding the derivatives of the normal unit vector to a surface. Today we will discuss some problems based on Weingarten equations. So the first problem is deduce the following from the Weingarten equations. First part is H into the scalar triple product of the three vectors vector n, vector n1 and vector r1. This is equal to em minus fl. Second, the product of H and the scalar triple product of the vectors n, n1 and the vector r2 is equal to fm minus gl. Third part, H into scalar triple product of the vectors n, vector n2 and vector r1 is equal to en minus fm. And the fourth is the product of H and scalar triple product of vector n, n2 and r2 is equal to fn minus gm. Here n1 is the partial derivative of the normal unit vector n with respect to the parameter u. R1 is the partial derivative of vector r with respect to parameter u. N2 is the partial derivative of the normal unit vector n with respect to parameter v, and r2 is the partial derivative of vector r with respect to parameter v, and EFG element, these are the fundamental magnitudes. So in order to prove these parts, let us start from Weingarten equations. Now the first Weingarten equation is h square into n1 is equal to fm minus gl into vector r1 plus fl minus em into vector r2. Now taking cross product by vector r1 on both sides of this equation, if we take cross product with r1 on this side, we get this term, and here the cross product with r1, here also the cross product with r1. Now because r1 cross r1, that is 0, so this term will become 0, and here we are left with fl minus em into the cross product of vector r2 and vector r1. Now from the left hand side we can take h square on the right hand side, so we get the value of n1 cross r1, which is em minus fl divided by h square into r1 cross r2. Now let us start from the first part which we are required. We are to find the value of the product of H and scalar triple product of vector n, vector n1 and vector r1. Now by definition of scalar triple product, this product is given by n dot n1 cross r1. Now the value of n1 cross r1 we have obtained already in the equation 1. So from here, substituting the value of n1 cross r1 here and putting value, we get h into the scalar triple product of vector n, vector n1 and vector r1 is given by h into n dot. Here we have put it the value. Now this h square is cancelled with this h square, and n dot n, because n is normal unit vector, so n dot n, that will give 1. So we have obtained the first deduction. Now to prove the second part, again we will use the same Weingarten equation, and now in this case we will take the cross product by the vector r2. So in this equation, if we take cross product by the vector r2, on the left hand side we get h square n1 cross r2. On the right hand side we get fm minus gl into r1 cross r2, and this term will contain r2 cross r2, so that will vanish. So from here we have obtained n1 cross r2, which is fm minus gl divided by h square into r1 cross r2. Now let us start from the part which we are required. We are to find the scalar triple product of vector n, n1 and vector r2 with the product with h. Now putting the value of this scalar triple product here, we get h square is cancelled with h square, and n dot n is again 1, so we get the value fm minus gl. Now to prove the third deduction, we will use again the second Weingarten equation. Second Weingarten equation is h square n2 is equal to fn minus gm into vector r1 plus fm minus en into vector r2. Now let us take the cross product by vector r1 on both sides. If we take cross product here with vector r1, we get this. Here fn minus gm into r1 cross r1 plus fm minus en into r2 cross r1. Now because r1 cross r1 that will be 0, and from this term because r1 cross r2 that is h into vector n, so r2 cross r1 that will be minus h into vector n. So from here we can obtain the value of n2 cross r1, which is en minus fm divided by h square into hn. Now according to our requirement, let us consider the term h into scalar triple product of vector n, vector n2 and vector r1. Now putting the value of n2 cross r1 here, we get en minus fm divided by h square into these two terms. Now h square is cancelled with h square and n dot n is 1. So we are left with en minus fm. Now the last deduction. In order to find the last deduction, we again use the second Weingarten equation and we'll take cross product by the vector r2 now. So if we take the cross product by vector r2, we can find the value and put in the Weingarten equation. Now h square n2 cross r2 that is equal to fn minus gm into r1 cross r2. Now again putting the value of r1 cross r2 and dividing by h square. So we get n2 cross r2 is equal to fn minus gm divided by h square into r1 cross r2 is h into vector n. Now let us consider the term h into the scalar triple product of vector n, vector n2 and vector r2. Now by definition of scalar triple product, this product can be written as n dot n2 cross r2. Now substituting the value of n2 cross r2 which we have obtained already, we get h into vector n dot fn minus gm upon h square into h into vector n. Now h square is cancelled with h square and n dot n is 1. So we get the value fn minus gm. So these were some deductions which you obtained from Weingarten equation. Now the next problem is if L, M and these fundamental magnitudes vanishes everywhere on the surface, then we have to prove that the surface is the part of the plane. In order to prove that the surface is part of a plane, we will have to prove that the normal unit vector to the surface that is constant vector at every point of the surface. So in order to prove that that is a constant vector, we will have to prove that that is independent of the parameters u and v. So in order to prove that, let us start from the definition of the fundamental magnitudes L, M and N. We have already derived the values of L, M and N in the previous articles. L is given by minus n1 dot r1, M is given by the two terms, either we can use minus n1 dot r2 or we can use minus n2 dot r1, and N is given by minus n2 dot r2. Now because we are given that L, M and 3 coefficient vanishes, L is 0, M is 0, N is 0. So from here if L is 0, n1 dot r1 will be 0, M is 0, n1 dot r2 and n2 dot r1 will be 0, N is 0 means n2 dot r2 is 0. So we have obtained these dot products is equal to 0. Now because vector r1 and vector r2, these are the tangential vectors to the surface, they are not equal to 0. So if this dot product is 0, either the vector n1 will be 0 or these two vectors will be perpendicular. In the same way, if the dot product of these two vectors is 0, either n1 will be 0 or these two vectors will be perpendicular. In the same way from here, either n2 will be 0 or these two vectors will be perpendicular. Now let us check the possibilities. So if we have n1 perpendicular to r1 and r2, in that case the vector, because n1 is perpendicular to r1 and r2, so that will be parallel to the cross product of these two vectors, and by definition this cross product is h into vector n. Now so from here we have obtained that vector n1 and vector n are parallel vectors, but as we have already discussed, because vector n and vector n1 are perpendicular vectors, because n is a constant vector, this is normal unit vector, its magnitude is constant, and we know that if the magnitude of a vector is constant, then its dot product with its derivative, that is always 0. So these two vectors are perpendicular vectors, so this condition is not possible here. So we are left with only one possibility, so n1 must be 0. Now what is n1? n1 is the partial derivative of vector n with respect to parameter u. So if that derivative is 0, so vector n is independent of the parameter u. In the same way, from this equation. From this equation, we have vector n2 is 0, means the vector n is independent of v. Thus, we have proved that vector n is independent of the parameter u as well as parameter v. It means vector n is constant vector at every point of the surface. So, we can say that the surface is a part of plane. Now, let us discuss one more example based on these results. The next problem is deduce h into n cross n1 is equal to m into vector r1 minus l into vector r2, and second part is h into n cross n2 is equal to n into vector r1 minus m into vector r2. We are to deduce these two results. So let us start from the definition of normal unit vector. Now by definition, normal unit vector to the surface is given by r1 cross r2 divided by its magnitude. Now because this is h, so from here r1 cross r2 is equal to h into this vector. So we have obtained this result. Now let us differentiate this with respect to u partially. So by using the product rule, h as it is, the derivative of n with respect to u, that is vector n1, and plus h ka derivative h1, and as it is here again by using product rule for the cross product of vectors. So derivative of r1 with respect to u, that is r11, and derivative of derivative of r2 with respect to u, that is r12. Now taking cross product with vector n on both sides of this equation. So if we take cross product with vector n on both sides of this equation, we get h into n cross n1. Here n cross n, that will be 0, so this term will become 0. Here taking cross product with vector n, and here also taking cross product with vector n. Now on the right hand side, we use the definition of vector triple product of these three vectors and these three vectors. Here, using the definition of vector triple product, the dot product of these two vectors into this vector minus the dot product of these two vectors into this vector. From here also, by definition of vector triple product, the dot product of these two vectors into this vector minus the dot product of these two vectors into this vector. Now, using the definitions of LMN, by definition n dot r11, this is L, n dot r12, that is M, and vector n, because that is normal unit vector to the surface, so that is perpendicular to the tangential vectors r1 and r2. So n dot r1 is 0, n dot r2 is 0. So using these four results here in this expression, we get the required result, which is equal to minus L into vector r2 plus M into vector r1. Now to prove the second part, again we will differentiate the same equation with respect to the parameter v partially. So again using the product rule, here h as it is, the derivative of vector n with respect to v, that is vector n2, plus the derivative of h with respect to v, that is h2, and as it is here the derivative of r1 with respect to v, that is r12, and derivative of r2 with respect to v, that is r22. Now taking cross product with vector n on both sides. Here if we are taken cross product with vector n, we get this term. Here taking cross product with vector n, we get this term. Here again taking the cross product with vector n. Now again using the definition of vector triple product, this vector triple product is given by n dot r2 into this vector minus n dot r12 into vector r2. Here this vector triple product is given by n dot r22 into vector r1 minus n dot r1 into vector r2. Now again using the four results, n dot r12 is m, n dot r22 is n and r2 are perpendicular vectors, so their dot product will be 0. n and r1 are perpendicular vectors, so their dot product will be 0. Using these four results here, we get the result, which is minus m into vector r2 plus n into vector r1. So these were some examples which were based on Weingarten equations and the definition of normal unit vector to the surface.